All right. Hi, everyone. I'm Josh Grochow from Boulder. The thing that I wanted to, well, I was going to say introduce, but just sort of already introduced it, elaborate on, is multi-way or higher order interactions. And you won't find any papers of mine on this, at least not yet. Hopefully, soon. This is based on joint work and conversations with a bunch of people. One who I want to highlight in particular is Yoav Kalas, who was a postdoc at SFI with me. We were office mates, I think partially by design. This was something that we've been talking about since the first year we were there. So we typically model complex systems by trying to understand the interactions between the constituent parts, whether that's people in a social network or entities in an economy or a city or proteins. And very frequently, we do this by modeling their pairwise interactions, right? Even when we use networks, the fundamental object in a network is an edge. It's modeling an interaction between two components, and then you have many of these. So for example, in the patent network, a node in this network is a technology code. So every patent has a list of codes saying what technologies are used on it. There can be many, there could be one code or many codes on any given patent. And there's an edge between them if two codes are present on the same patent. OK. So the question is, if you see this in the patent network, what is this? And now I'm hoping that coffee has kicked in. I'm actually asking you, what is this?
Looks like a triangle to me.
Yeah, OK, it's a triangle. But in the patent network, right, we said nodes are technology codes, and edges mean that they occur together on a patent. So maybe it means this. Maybe there are 3 different patents, and these codes each occur in pairs, right? Or maybe it means this, where there was one patent that had all 3 of these technology codes on it. And the point is, just from the network, you can't tell. But if I allowed myself a multi-way interaction, not just an edge, a pairwise interaction, and I had something like this, and now I erase the labels, well, now you can tell the difference between those 2 situations. Now, this seems like, oh, this was just sort of an issue of how do we represent the data. But the issue of multi-way interactions is much deeper than that. So here's a very simple example. Imagine you have 3 binary variables, 0 and 1, and you observe them with these probabilities. And the regularity to notice here is that the number of 1s that you see is always even. OK. Here, if you look at any pair of variables, they're completely independent. All 4 possibilities for that pair occur with equal probability. So there are literally no 2-way interactions here. There's not even a shadow of the 3-way interaction in the 2-way interactions. But there's some 3-way interaction governed by the number of 1s is even. Right? OK. So we talked about probabilities. We talked about networks. That probably covers the vast majority of things that we study. But lest you think that this is merely restricted to those domains, it sort of applies everywhere. So on the left here, we have the Borromean rings. If you delete any one of them, the other 2 can be pulled apart. So if you just ignore the red ring, you'll see the green ring is entirely on top of the blue ring. They can just be pulled apart. And that's true for any one you delete. But the 3 of them cannot be pulled apart. And you can actually build this and play with it and see that you can't pull them apart. You could also imagine that you have here, say, a description, again, of 3 variables and the allowed values that they can take, right? And say it's restricted to this sort of box-like shape. If I look at any 2 of the variables, I don't see any restriction. They occur in a square, right? I can vary them independently. But when I see all 3 variables, there's suddenly this restriction that you can't get near the corners of the box. So again, in both of these cases, you have no pairwise interactions, but you somehow have 3-way interactions. So an important question in sort of any system is how multi are these irreducible multi-way interactions? At what levels of the system do they occur? Okay. And this question has lots of implications, but in particular for, we think sort of complex systems, probably the interactions occur at multiple different levels. It also has implications for levels of description, right? If sort of all of the 5-way interactions are already described by the 4-way interactions, well, you don't need a new level of description at the 5-way interactions, right? You can think of each of these irreducible interactions itself as a little sort of mini emergent phenomena, but you can also think more globally about what this tells us about emergent phenomena. And then the one that I'm going to spend the next few minutes talking about is how hidden variables relate to complexity and what this has to do with multi-way interactions. So it's a pretty universal phenomenon that hidden variables create complexity, or at least they create the appearance of complexity. And maybe when you can't access the hidden variables, is there really a difference between complexity and the appearance of complexity? I don't know. Okay. This occurs all over. In geometry, you can have a smooth, high-dimensional surface that when you project it down becomes not smooth, right? So the picture on the right here, the surface is still smooth, but when you look at its shadow in the plane, you see these weird corners and self-intersections. In computational complexity, and I assume that probably most of you don't know what P versus NP actually is, but you've at least heard of it. NP is basically just P with hidden variables. And this is not a hand-wavy analogy. You can actually make that like a formal definition. And so the whole P versus NP question is essentially the question of what is the power of hidden variables to create complexity? And then this also applies to many of the other things we've talked about. Probability, convex bodies, also quantum states, and many other things. OK, so what does this have to do with multi-way interactions? Well, you can ask, how many hidden variables do I need to eliminate all of the multi-way interactions, let's say, except for the three-way interactions? Like, I want to allow some interactions. And so here, this is just a larger version of the example we saw before. So now I have 4 binary variables, and the restriction is still just that the number of ones you see is even. OK, so there are no two-way interactions here. There are no three-way interactions even. But there is a 4-way interaction, right? That across the 4 of them, the number of ones you see is even. OK, and I claim that here you can get away with 2 additional variables. And now all of the interactions are 3-way. There's no 4-way interaction anymore. So the interactions are, my new variable b is just the parity of my first 2 variables, x and y. My new variable c is the parity of the second 2 variables. And then my next constraint is that the parity of b and c has to be even, which is a 2-way interaction. So I had b is related to x and y, that's a 3-way interaction. C is related to z and w, that's a 3-way interaction. And b and c are related, that's a 2-way interaction. OK, so something about you can use the concept of higher order interactions to get at what does it mean to need a certain number of hidden variables to explain the data, and to explain the data at what level. OK, and now I want to do a little aside, and then we'll come back to the thing in a minute. There are sort of 2 dominant tools for analyzing complex systems, right? We have many different models, but there are 2 dominant tool sets. There's probabilistic and computational. Computational not in the sense of like I analyze it on my computer, but in the sense of sort of what Jess was talking about, where the model itself comes from computer science, right? So on the probabilistic side, you have things like statistical inference, statistical mechanics, information theory, and generally speaking, it's about correlation. And on the computational side, you have things like symbolic inference and automata and generative grammars and Turing machines and Petri nets and Boolean networks and all of these things. And OK, I put this question mark. It's sort of more about mechanism in the sense of if you have a computational model, it tells you, oh, if this is true and this is true, then this is true, right? So it's not just correlation. It's sort of closer to causation. It's not necessarily the same thing as mechanism when we talk about, I want to understand sort of what's the global mechanism that governs an economy, right? But it's sort of more in the direction of mechanism than it is in terms of correlation. And these 2 are often very hard to use in combination. Right? You can sort of either analyze a system statistically or computationally. Right? Now, in Jess's talk, we saw some examples where you start to combine the 2, but that's pretty rare. So one of the cool things about multi-way interactions is that this is another place where these 2 things come together, and particularly in this question, how many hidden variables do you need to get rid of all of the higher order interactions? And the answer, which I proved with an undergrad, Sam Schlesinger, a couple summers ago, is that the minimum number of additional variables you need to get rid of all the higher order interactions is the same, up to some small fudge factor, as the non-deterministic circuit size. So circuit here in the sense of Boolean circuit with and, or, and not gates. Non-deterministic, I don't have time to get into what that means, but the point is, here we have this relationship between what is essentially a probabilistic question, how many hidden variables do you need, and a purely computational question, what's the circuit size? All right, so just to tie it up, Multi-way interactions sort of occur everywhere. They apply to probability distributions where these kinds of questions are often studied in information geometry, networks, circuits and algorithms where, by the way, like also if you have, say, a deep neural network that you're interested in, you can look at the nodes in the network and say, what are the levels of interactions between the nodes in that network? You know, are some high-level interactions necessary for it to do its job well or not? What kind of things do we see in practice? Quantum entanglement, many areas of math. So we already saw an example of topological links, but this also applies to, for example, interactions between prime numbers, groups in algebra, combinatorics. And I'd like to think that probably this applies to just about everything. And I'd be very happy to talk to anyone about that. And I'm especially happy if you think it doesn't apply to your area. I'm especially happy to talk to you and see if we can maybe fix that. So thank you.